Good afternoon, my name is Sergio Ricci. I'm co-chairing this session together with Chris Atkinson, that is the responsible of the program committee. I'm happy to see also different faces from this morning because this is the second part of the special session on high aspect ratio wing. We decided to introduce this topic because probably the configuration of the future aircraft trying to match the zero emission constraint will be based on high aspect ratio wing. That for sure automatically is able to guarantee some reduction of induced drag, but automatically generate other side problems. This morning we had a session dedicated to aeroelastic issues mainly. This afternoon we have another session open to more different kind of problems. I want to introduce the first speaker, good friend of mine, colleague from ONERA, Meheut, that has a long experience from different companies, ONERA, Dassault, and now still again company. He got the master degrees in mechanics in the INSA, National Graduate Engineering School in Rouen, the master degree in energetic combustion in Korea Laboratory 1, France, and finally the PhD in fluid dynamics and aerodynamics at University of Science and Technology in Lille, France. Please.
Thank you, Sergio, for the introduction. So I am going to present a common work done in the frame of the Upwing Clean Aviation project between ONERA, the Technical University of Delft, and University of Stuttgart, with many different people and many different colleagues. So this talk is dedicated to the design of a STRUT-BRACED dry wing configuration for LH2 power aircraft. So just a few words, you probably already know all this, as we are at the end of this Congress. So why a STRUT-BRACED wing? So the first obvious thing is the reduction of the induced drag, thanks to increase of the aspect ratio. Just for instance, if we are able to double the aspect ratio from 10 to 20, we are able to reduce by a factor of 2 the induced drag, which represent today about 1/3 to 40% of the total drag. The drawback is, of course, the mass of the wing and the bending moment you have as the root. So the idea, when you increase the aspect ratio, is, of course, to add a strut to reduce this bending moment. I will not detail more, just a few words about the history of the STRUT-BRACED wing. So it's not a new idea. So the first concept was developed in the 30s with the Henshaw aircraft, then the Hurel-Dubois in France. And on ONERA side, we start to work about 12 years ago on this concept with first so-called Albatros, which was a laminar wing concept with, I would say, limited aspect ratio at that time. Then we moved to the Harvard ONERA concept in the frame of the same name project. And then today we are working in the frame of the clean aviation on these LH2 power aircraft. You have also, of course, on the US, the X-66 concept then demonstrator by Boeing and NASA, and also the Cessna Sky Courier in 2020. So my presentation will follow this outline. So I will give a very short introduction to the Upwing project, then describe the overall methodology we have set up to do the sizing of this configuration, present the overall aircraft design process, and show some first results we obtained so far. So the Upwing project started in 23, beginning of 23, and will finish mid-26, gathered 24 partners, so industrial partners, RTOs, and academia and SMEs, and for a funding of almost 40 million euros. So in this project, the main objective is to develop, validate, down-select, mature, and down-select all the key technology that will enable to have a very efficient wing for the next generation of SMR aircraft. So in this project, we are covering two main challenges with two main configurations. So the first one is, I would say, the less aggressive one, which will be, so we will have very high aspect ratio wing, a configured aircraft that will use SAF, and the objective is to improve the overall efficiency by 10 to 13% with this configuration, which at the end will be more mature than the second one, which is the one which is of interest today for this presentation. The objective is to exploit non-dropping fuel like liquid hydrogen, and the objective is to further increase the aspect ratio of the configuration, for instance, by adding a strut, and have an improve in terms of efficiency up to about 17%. So this is exactly the presentation, so we'll focus on this STRUT-BRACED dry wing concept for LH2 power aircraft. So in terms of methodology in the project and to develop this concept, we have 3 design steps. You can see here on the bottom left. These different steps, between the different steps, the objective is to progressively increase the maturity of the different tools we consider in our process, but also better take into account the different interaction we can have between the different elements. For instance, as we want to have a large exploration of the design space, the idea is to study different kind of option for the engine, so UHBR or USF. So of course, when you consider USF, you have to take into account the interaction between the blade and the wing. And we want also to compare cantilever, classical cantilever with a strut-braced wing configuration in order to see the potential of the two concepts and the limit of the two concepts. For this, we have quite obvious 3 disciplinary streams. So the first one, of course, is the structural sizing. And here, as we have a dry wing concept, one of the key points is also to exploit this, the fact that we do not have any fuel anymore in the wing, so to perform some topology optimization in order to change the paradigm of the structural design. Then we have the second stream, which is dedicated to movable design that will handle all end-wing qualities, but also the different load elevation strategies that we can set up in these different configurations. Then the red one is the aeropropulsive design, so aerodynamic coupled with the engine integration of the 2 engines. And to make the link with these high-fidelity tools and modules we are developing in the first 3 design streams, and to feed up our overall aircraft design process, we will use surrogate models based, so multi-fidelity surrogate model based on high-fidelity data and based on the dedicated parameterization for the different configurations. So here today I will focus only on step 1 and the result we obtained so far. So regarding this step 1, we have defined what I call a 5-step multidisciplinary and multi-fidelity design approach. So first, in order to explore our design space, we have defined a nested multi-fidelity design of experiment, which is based on a dedicated parameterization that I will show in the slide after. So we have more than 1,000 configurations in this initial design of experiment. Then we do the initial sizing of all configurations based on the level 0 method we have natively in our fast OED tools that I will describe afterward also. The third step is the design and the performance assessment using the high fidelity tools we have, so for different disciplines. So you can see here we set up different modules for the different disciplines. So for aerodynamics, we have the empirical formulation which are calibrated towards run simulation, but we will also use LR simulation and run simulation depending on the configuration. For the structural sizing, we have 4 levels. So the first one is a B model, the one which is natively integrated in the process. We have then a simplified finite element model. The third one is more detailed finite element model with an aeroelastic coupling. And then the final one aims at performing topology optimization and also optimize the stacking layer, the composite that we can use for this kind of configurations. And the last one is for so the movable and the load alleviation capability of the configuration. So we have first empirical formulation, and then we will use panel methods to compute the different aerodynamic performance that will be used then to size the different movable control surface and define the ability to perform load alleviation. Then the fourth step is the creation of the multi-fidelity disciplinary surrogate model based on the low and high fidelity for the 3 disciplines that then will be integrated and used in the OED process where we will resize all configuration of the DOE. And then we will be able to exploit our design space. So in terms of parameterization, for the first step, we have defined 11 design variables. So you have, for the 3 first are for the wing, where the main objective is really to have the main parameters that will affect the global performance. The first one is obviously the aspect ratio of the wing, which will move for the strut-braced wing from 18 to 28, so we try to be quite aggressive. For the cantilever wing, we have the same exercise, but we are between 10 and 28. We have also the thickness at the root of the configuration and the location of the kink. Regarding the strut, we have 6 parameters, so as you can see here. So the first one, which is quite important, is the length of the span of the vertical part. You can see the L1, you can see on the right, We have also a vertical part where you have a small elbow at the junction between the wing and the strut. We have, of course, the location of the wing strut junction, which will be a very important parameter. And then we have some other parameters that define the local chord of the strut. Then we have also one parameter for the fuselage. It is the height of the fuselage. As we are considering LH2 configuration, we will have two LH2 tank at the rear of the configuration. And so to avoid to have a too long fuselage, we think that having not only one SL for this configuration, but two SLs could be an option in order to avoid a very, very long fuselage for this LH2 power aircraft. Then we have also one parameter for the engine in order to be able, for this first step, to consider UHBR and USF together with different mass, but also different SFC we may have in the process. And also we have one factor at the end, which is I call load alleviation factor, which aims at reproduce the fact that we are able to reduce the load on the external wing. It's a very simple way of tackling the problem first, but just to see the sensitivity we may have with the beam model integrated here. So very quickly, the fast OAD process. So it is developed at ONERA in collaboration with ISAE SuperAero. So it is open source. It is based on OpenMDAO and enabled to automate multidisciplinary analysis and optimization for different kind of configuration and perform some optimization. It includes natively what we call level 0 disciplinary models for all main disciplines we have in classical OAD process. And thanks to his modularity, we are able to quite easily implement or integrate higher fidelity tools through direct coupling or via the use of surrogate models. So regarding the configuration, I just summarize here the pillars of the configuration, which are the one used in the SMR pillar of up in clean aviation. So we have 239 packs, a range of 2,500 nautical miles, and a cruise Mach number of 0.78. In terms of structural sizing, for the LH2 tank, we have decided, based on previous study made internally, to choose a gravimetric index of 0.5, which is quite aggressive, but it's, I would say, a first assumption. Regarding the structural sizing, our objective on this configuration was also to study different advanced technology we may have in the future on the configuration. So we do the sizing for two kinds of material, one classical aluminum and one which is a so-called black aluminum, which represent an equivalent to an isotropic composite for the wing and for the strut. So here the result I will present detail all analyze all the results of the initial steps, so using a surrogate model, so using all level 0 modules we have in the fast OAD process. I will compare results between the strut-based wing configuration and the cantilever one, and will detail some technology effect we may have, so load alleviation strategy and different material. And I will show you some very first results regarding the high fidelity analysis. So here on this picture, you have two pictures. So on the left, you can see on the horizontal side the wing aspect ratio. On the vertical side, you have the location between the wing and the wing strut junction in terms of alpha wingspan. And you can see the mission block fuel of the configuration in terms of LH2. So the values are quite small compared to kerosene. It's about 1/3 of what you have classically on the A320, I would say. So what you can see quite obviously is that you have a hotspot and a clear minimum on the left, where it represents a load alleviation factor of 0, so we do not have any aggressive load alleviation strategy in this case. So the optimal point is with an aspect ratio of about 24 and a location and a wing strut junction at about half of the span of the configuration. When we try to add some smart load alleviation strategy, we see the trends, a clear trend which can be easily explained. First, so you have a reduction, of course, of the block fuel, and you see that the minimum move towards the right, and the bottom. It means that we are able, thanks to load alleviation, to increase the optimal aspect ratio, but also we reduce the length of the strut. As we have less loads on the external wing, we do not need we need a shorter strut for the same configuration. I just show you some results regarding the maximum takeoff weight. So you can see exactly the same part of the design space. So wingspan aspect ratio versus wing strut junction location, and load elevation factor of 0 on the left and 0.3 on the right. So what we can see here is that whatever the aspect ratio is, we have a minimum in terms of maximum takeoff weight for wing strut junction, which is at about 60% of the span. When we had some load aviation strategies, we can clearly see that we are also able to reduce the length of the strut, so the minimum is with a shorter strut, as explained before. This strain on the maximum takeoff weight is due to modification of the wing and strut weight, as you can see here, where we have more or less the same trains as for the maximum takeoff weight with the same location of the minimum and the same sensitivities. Now, if we look at the cruise lift over drag, what you can see is quite logical result, as expected. So when you increase the aspect ratio, you have a strong increase of the lift over drag. You can see if you move from the left to the right, and if you move from the top to the bottom, you can see a reduction of the length of the strut, so you have a reduction of the friction drag, so you are able to have a more important cruise lift over drag in cruise. And we have more or less the same value for with and without and with load alleviation strategies. So here you have the same result for the cantilever wing, so in terms of block fuel. So what we can, so in terms of design space, the horizontal part is a wing aspect ratio as for the strut-braced wing, but the vertical axis is the relative kink location. This factor will be quite important as implicitly it changes the thickness we have on the wing, because at the root we have 13% of thickness, relative thickness, and 10% at the tip. So when we move the kink location, we artificially change the thickness along the wing. So what we can see in this case is that the sensitivity of the block fuel with respect to this kink parameter is relatively small compared to what we have with the wing aspect ratio. And we see that we have a minimum which is for a value of about 16 without aggressive load elevation strategy, which may be quite optimistic, I would say. And when we had more load elevation in our process, we further increased the minimum or the optimal value for the, in terms of aspect ratio, which moved up to about 19 here. So in this figure, I try to summarize the different results we have. So you see 8 curves. The 4 on the left represent the cantilever wing, the 4 on the right represent the strut-braced wing. And for the true configuration, you have the effects of the technology effect. So the green curve, full line, represent the classical technology, so no aggressive load alleviation and a classical aluminum. Then you have the black curves that represent the fact of using a black aluminum or an equivalent composite material. Then you have the 2 dotted lines, we represent the fact of having an quite aggressive load alleviation strategies, so with the green and the black curves. And so you have the same for the strut-braced wing on the right. So what we can, and what I have to add also, that here we do not fully exploit the design space, as the strut characteristics are not optimized for the strut-braced wing. They are kept constant. What you can see here, so it's the evolution of the mission block fuel with respect to the aspect ratio. So we see that for the cantilever wing, we have a very strong dependence and strong effect of the different technology we can add. And for instance, when we take the 2 extreme curve, we have a decrease of the fuel burn of about 10%, which is relatively important. And we obviously see also that when we had more and more advanced technology, we are able to improve globally the fuel burn, but also we move we increase the optimal aspect ratio of the configuration. We have the same train for the strut-braced wing, but the gap or the difference between the 2 extreme configuration is only about 2 or 3%. So it means that the effect of new technology is really less important on the strut-braced wing than on the cantilever configuration, where you have very strong sensitivities to the aspect ratio, as you can see here. So on the next slide, I will try to give you some more precise figure in terms of performance improvement, and I will compare the different optimal configuration, so the one which are on the minimum of each curve, with a reference that I decided it was the one on the left with classical, I will say, technology assumption from today, and with an aspect ratio of 10. So you can see on this plot these 8 configurations, so 4 for the cantilever, 4 for the strut-braced wing, and you can see the difference compared to the reference for different function of interest. So in orange, you can see the block fuel, maximum takeoff weight in gray, the empty weight in yellow, in blue, the wing plus strut weight for the strut-braced wing, and the cruise L/D in green. So what we can see on the cantilever wing for all configurations, so we see that the block fuel reduction is increasing when we add more and more advanced technology, but we see that these benefits are due to a strong gain in terms of aerodynamics, about 20% for most of the configuration, but we have a quite important penalty in terms of wing and strut weight, or wing weight for the cantilever, which is, I would say, an expected value, but in terms at the end of empty weight or maximum takeoff weight, the difference is limited, and we have at the end an important gain in terms of block fuel. When we look at the strut-braced wing, we see that at the end we have less gain in terms of aerodynamic, which is about 15% for most of the configuration, but we have some additional gains thanks to the structure, and in terms of wing weight, we have a reduction of about 5 to 10% depending on the configuration. So we see that even at the end, both configurations, when we look at the previous slide, provide more or less the same absolute value. It really depends where the technology you see. It's for really different reasons. This slide aims at showing the effect of the material on the final result. So you have the 2 cantilever configurations, so for the 2 load alleviation factor on the left and the 2 for the strut-braced wing configuration. So what we can see here is that for the strut-braced wing, the benefits we have or the difference we have is almost independent of the load alleviation factor we can put if we see the impact of the material, which is not the case for the cantilever wing, where we can see a quite important sensitivity when we couple material and advanced load alleviation strategies. The same thing for the load alleviation. So I compare, it is the difference between the 2 configurations for the load alleviation strategies, so with aggressive load alleviation strategies and without load alleviation. So we have exactly the same results compared to the effect of the material. It means that for the strut-braced wing, the impact, whatever we use, aluminum or black aluminum, is the same, and we have some important difference for the cantilever wing, which is very sensitive, to these different technologies. Just a few words about the high fidelity result we have. So first, in terms of aerodynamics. So among the more than 1,000 configurations, we perform about 80. We select 80 configurations, and for this 80 configuration, we do the polar for the in EULER using the our EULER CFD code. So in cruise condition, but also at a higher Mach number. And for 20 configuration, we do the same using a RANS simulation. So you can see on the left the trains we have for the different drag coefficients. You have so the total drag in red, the friction drag in pink, the induced drag, so for RANS and EULER in gray, the viscous pressure drag in orange, and the wave drag for EULER and RANS in blue. So the main message here, we see that clearly for the induced drag, we have exactly the same trains between EULER and RANS, which is expected result, but it's good to be checked. And for the wave drag, we have also the same sensitivities, even if we have an over-evaluation of the wave drag due to with EULER, which is also expected result. Just a few words about structural sizing. Here we compare the result we have with level 0 method and level 1 that was presented by one of my colleagues yesterday. Here we see more differences. You see in the same, so wing aspect ratio on the horizontal axis and wing strut junction on the vertical axis. You see that we have some important effect and shift of the minimum value we obtain in terms of wing strut junction for both models. That will probably strongly impact the result we have at the end using higher fidelity. And so just in conclusion, so the main takeaway regarding the methods and tools we have developed, so we have defined and implement here a complex multi-fidelity and multidisciplinary design process with our partners, so TU Delft and University of Stuttgart. we have developed the different tools for the high fidelity part, and we are able to use advanced surrogate modeling approach to combine the accuracy of high fidelity and be able to explore the design space offered by this dry wing configuration. In terms of result, we were able to compare the result we obtained on the cantilever one with the strut-braced wing concept, where we see that we may have some similar results which strongly depend on the technology we have. Compared to the reference aircraft, we obtain gains which are about between 15 and 17% in terms of fuel burn or LH2 consumption here. And so we see that at the end, so the cantilever configuration is very sensitive to the different technology efficiency, and the strut-braced wing clearly less. So with the current technology, the strut-braced wing seems more promising than the cantilever, but with more advanced technology, the cantilever may be more efficient, but in this case, it means that we will have also to certify very complex technology for a future aircraft. So it may, so the paradigm is quite different between the two configurations if we want to have an efficient one. And so regarding the next steps, so in short terms, is to finish the overall process in order to define, to exploit the design space using high fidelity tools and be able to define an optimal configuration based on these first steps. Then the second step is to improve the ability of the different high fidelity modules. So first, for the aerodynamic, taking into account the interaction between the USF and the wing via a body force approach that will be used in our CFD code to perform aeroelastic analysis for two configuration. For the structural design, one thing which is really important is to increase the number of load case, but also the way we are able to model the effect of load alleviation strategies. We'll also perform topology optimization in order to benefit from the design space offered by the dry wing. And then we'll, in the next step, also do resize the different movable we can have on the configuration and not fix it a priori. And also, with the movable sizing, exploit the design space offered by the dry wing. And last slide, I would like to acknowledge Clean Aviation for the funding of these activities.
Thank you, Mikhail, for your very nice presentation. We have time for one or maybe two quick questions.
Sebastian Wöhler from German Aerospace Center. Thank you for the presentation. It was very good. Concerning the cantilever wing, you mentioned that you have complex systems that are hard to certify. Could you elaborate on that?
I'm not a specialist, but for me, it will mean to be able to perform gust load alleviation, for instance. So it means to have, for instance, a LiDAR which will be able to detect the gust that will arrive on the aircraft, maybe 1 second before. You need time for the different control surface to act and to reduce the load you have when you have the gust. What I mean by this certification, it's yeah.
The first. Maybe. Just start with the same.
Hello, Thomas Streitiger, Braunschweig. I have a question. Is in the project also the high lift considered?
Not yet here. They are considered through empirical formulation in the OED process, but we did not design any high lift movable or
Yes,
flap here.
Because I mean, to have a high lift devices for a strut-braced configuration, this will be complex, but much more complex than
It really depends where the strut is, the junction with the wing is. Yeah.
Thank you.
Did you consider?
Yeah, sure.
Sorry,
Jonathan.
Did you consider the buckling of the strut?
Not in the BIM model, but it will be done in the high fidelity tools. Yes.
Thank you so much. So it's time for you, Chris.
Okay, so I think now we have Dr. Tobias Wunderlich. Tobias, do you want to come up? So Tobias has his diploma in engineering from RWTH Aachen, and then in 2013 completed his dissertation at the Faculty of Mechanical Engineering at TU Brunswick, Germany. Okay, so Tobias, over to you.
Yes, thank you very much for the introduction, and also welcome from my side. Today I would like to present the results of my research in the field of high aspect ratio wings of highly efficient long-range aircraft. So we make a little bit step from the short to the long range. So now I would like to start my presentation with the DLR's aviation research strategy. So the vision is, we heard a lot of times here, is the zero emission aviation. And this talk is focused on the energy efficient aircraft. And the vision is that we have to reduce the energy requirement up to 50%. And second thing I think is important is also the digitalization, and we would like to twice the innovation speed. This means that we would have higher speed in the design of new aircraft configuration, also in the certification, and also the production. So now I would like to come to the highly efficient long-range aircraft, and the target is to decrease the fuel consumption, and the fuel consumption depends on the payload ratio for given range and payloads. So I've only this formula, so this is just part here, and the second one is the fuel mass ratio for the cruise flight, and here this is the fuel mass, and the range here is the sum of the range in the climb flight phase and the cruise segment, and also in the descent phase. So I think it's important to think about the fuel mass per payload and range. So I think it's important to select this as an objective. So, and what are the key performance indicators? The key performance indicators for the fuel consumption reduction are on the one side the lift to drag ratio, and on the other side the wing mass ratio. So now I would have a deeper look to the characteristics of high aspect ratio wings, and I have some four points here with me. The first and the main part is the reduction of induced drag. We have seen this formula in the presentation before, and what we see in this formula that it is possible to reduce the induced drag by increasing the span. But the second part, which is very important, is the span-wise lift distribution, which in the formula is considered with the Oswald efficiency factor. So here is a short table. This table I have done with based on handbook methods, but I think it's a good approach to see some things on this simple models. So if you think about a normal classical aspect ratio in the order of 10, then you have normally a center of lift within this area. And now if you increases the aspect ratio, you can done this in two manners. It's possible to have a same relative center of lift, and you could do this with the same absolute value of the center of lift. And this is important to think about, because the absolute value of the center of lift, there's some similarity with the wing root bending moment, and if you look then in the results, that if you look at the Oswald factor are the same if you have the same relative value of the center of lift, but you have a similar absolute value of the center of lift, then your Oswald factor decreases, and then your improvement in the lift to drag ratio is also reduced. So I think that's important to understand. So if we look at ultra high aspect ratio wings with an aspect ratio increase in the order of 30%, then we see that if we have the same relative value of the center of lift, then we get an improvement in the lift to drag ratio in the order of 10 or 11%. But if you considering only that we have the same absolute value of the center of lift, then it's reduced to 3.3%. So that's one thing. The other thing is that we have also to have a look to the wing mass, and the wing mass is inversely proportional to the absolute thickness of the wing. And if the aspect ratio increases, then the root, then the chord length also decreases, and also for a given relative thickness of the wing, then the absolute values decreases, and then the wing masses increases. So that's also important to think about. And so then normally you get with increased aspect ratio and increased in structural mass. The third thing I would like to introduce here is that you have to consider the static aeroelastic effect. So, and if you have with increasing aspect ratio, normally your stiffness decreases, and then you see in the tip area or the outboard area of the wing that you have that your lift is normal on the surface, and then you get some side force, and you can't use the side force, so you have also a little bit a decrease in lift. So that's have to also consider, and I think it's also important in this area. And the last step, what I would like to introduce here, is that you have also a lot of geometrical constraints. And here's a picture. You have normally considering the integration of a high bypass ratio engine, and the diameter increases with time. So you have to consider this. And the other thing you have to consider is that also the main landing gear normally is integrated in the wing. And you have also the control surfaces. You need also some space for the control surfaces. And if the aspect ratio increases, you have some problems with the space in the wing. So then you have also considering all these geometrical constraints. So now I would have a look to some technologies which I consider in my studies. The first technology is the adaptive wing. Adaptive wing means that your wing adapts the lift distribution to the flight condition, and one part is the active maneuver load alleviation. And we see here some pictures. So if you fly a maneuver, then normally you have a lift distribution similar to the red line. And then if you're using your control surface to shift your center of lift more inward, then you could reduce your bending moment and reducing the loads. On the other side, it's also usable to use the control surface deflections for cruise flight performance improvements, that you adapt your span-wise lift distribution to the current flight conditions. It's also you can be done if you have a long range flight that the mass of your aircraft changes, and then you could adapt your lift distribution to get the highest possible lift to drag ratios. The second thing we're considering here is advanced structural concept with increased strain allowables. These are very aggressive values, and I'm using, or behind is a message, is a method based on a damage tolerance allowable calculation. And based on the studies, we have selected this very high values. And also we're considering a local buckling after limit load, known as post-buckling or something like this. And with all these technologies together, the stiffness decreases, and you see more deflections of your wing for a given load. And also, if with all these technologies, you get an increase in the passive maneuver load alleviation because the decreasing stiffness of the wing. And what the main target is not the reduction of the stiffness. The target is the mass reduction. And if you increasing your strain allowables, you see a significant mass reduction. So with this in mind, I come to the method of my optimizations. So for the aerial structural optimization, I'm using this process. And the process is based on a central description of the aircraft in CPEX. Here are the design parameters, and if you change the design parameters, your CPEX description of the aircraft changes. And then you go from the CPEX file, you go on the left side to the aerodynamic calculation, on the right side you go to the structural side. And on the aerodynamic side, you're using a mesh deformation technique to bring the changing of the geometry to your mesh, and this is you have to do this for all the considered flight and maneuver load conditions, because you have also considering the control surface deflection. And the control surface deflection are here considered by using a mesh deformation technique using the flow simulator. Here you have your run simulation is run in parallel, and on the right side you has there's a automatic structural model generation, and then you have here a structural analysis, and then you have here the fluid structure loop. Here the forces comes from the run simulation and goes to the structure, and from the structure you get then the deformations back to your aerodynamic mesh. Important is here that here on the structural part, it's not only analysis, it's also including the structural sizing. So the structural sizing is directly included in the fluid structure loop. And then you get your objective function after this coupling loop is converged in terms of the wing mass and also the lift to drag ratio for all the considered flight conditions. So this was this, and then we have a deeper look to our design task. The objective function is the minimization of the combined fuel consumption, and we are considering here three missions. We have our study mission with the highest weight factor and a range of 4,000 nautical miles with a Mach number of 0.83. With a given payload, and we have also a high-speed mission considering to get some off-design behavior to the optimization, and it's the same mission, but we are flying faster with 0.85. And then we have also a design mission with a relatively large range. And the payload is then a result because we have fixed the maximum takeoff mass. So if your wing mass increases, then you have less payload. So that's why I'm using this formula here. And then we here have also our design parameters. The design parameters describes the wing plan form with the leading edge sweep angle, with the taper ratio of the inboard and outboard wing. We have also included the twist distribution and also the control surface deflection angles and also the aspect ratio. So then we go to the next slide. So then let's have a look to the constraints. The constant maximum takeoff mass was fixed for this study, and we have also constant fuselage and engine masses here, and we have to consider the engine and landing gear integration as shown here on the picture, that we have enough space to the ground and all the stuff, and we have also considering that we have enough fuel tank volume in the wing. The center of gravity position was fixed, and we have a fixed set of maneuver load cases. We are only considering here 4 because it's a HiFi approach. And we would learn a little bit about what we're doing, then it's better to have not too much. We have a pull-up maneuver with 2.5 G, and we have a push-over maneuver, we have a roll maneuver, and we have a touchdown to consider the loads from the main landing gear to the wing. So now have a look to the results. So on the left side we see our baseline. The baseline based on some optimization of plan form and also airfoils, and then starting with this wing, optimized wing, then we introduce the new structural technologies I have shown before, and what we have done here is that we have used this wing plan form and airfoils, integrate the new technologies on structural side, and then make a twist optimization, and this is the result we're seeing here. So so the baseline has a conventional aspect ratio of 10.3. We have integrated the advanced structural concept, but we are using only a conventional maneuver load alleviation. That means we are only using the outboard ailerons for the reduction of the loads. So, and this is what we see. That's the results we see here for this. In the next step, what we see here is this wing with the highest aspect ratio I get with varying all my wing plan form parameters. This is the highest aspect ratio I see, which is a feasible design in terms of all the geometrical constraints. So, and then I make with this wing plan form, I made an integrate also the structural stuff, advanced technologies, and then I optimizing the control surface deflection for this aggressive wing plan form, and look how this ultra high aspect ratio wing performs. And what we see is that we get an improvement in lift to drag ratio in the order of 3%. Why this value is only so slow, we see on the next slides. And we see also a significant increase in wing mass in the order of 14%. And we have a similar fuel consumption as the baseline with a conventional aspect ratio. And the last result is the most important one, because it's the optimized wing plan form. So now we optimized the wing plan form with the same chain, and we are also include the adaptive wing. We optimize the control surfaces for cruise performance improvement and also to reduce loads. And what we see then, that is we get the same improvement in lift to drag ratio as the ultra high aspect ratio wing, and we only have a 6% increase in wing mass, and the overall result is that we could reduce the fuel consumption in the order of 2.5%. So now let's have a deeper look to the details of this result, and what we see here is on the upper side is that we see in black is the lift distribution, in blue is the lift coefficient distribution, and the black point here is the center of lift. So, and what we see is for the ultra high aspect ratio wing is that we have a lift distribution which is not optimal. And we have a very low Oswald efficiency factor. So that's one of the reasons that we don't see higher lift to drag ratios for the wing. And on the other side, we have a highly aerodynamic loaded outboard wing. And for the optimized plan form, we see a center of lift, similar to the baseline, and it's a better span-wise lift distribution. So now have a deeper look to the structural results. So what we here see is the results for the 2.5 G maneuver load case, and we see a very a good reduction of the loads by using the control surface deflection on the outboard. For the results of the higher aspect ratio wings, we also include the inner flap to shift the lift much more inward. And then what we see is that the absolute value of the center of lift is the same. The absolute value is the same for all three wings. And we have a look to the element thickness, that we see that with higher aspect ratio, the element thicknesses increases, and this is the reason for the higher wing masses. So now that's the last slide from the main results, which summarizes all the results. What we see here is the transfer of the aspect ratio for the fuel consumption in the left. In the middle, the lift to drag ratio for the study mission, and on the right, the wing mass ratio. And all the calculations I have done with the optimized wings. And what we see here is that we have an optimum in the order of 12. For an aspect ratio of 12, we get the best values in terms of fuel consumption. And the lift to drag ratio increases as expected, but then it's flattened out. So the reasons we have seen, and the wing masses increases linear here, as we've seen here. So and that's, I would shortly conclude. So the optimal aspect ratio is a result of the aerostructural wing optimization, and also the novel wing technologies shift the optimal aspect ratio to higher values. This is what we also can say. And in a short outlook, we would like to expand the design space. We would like to integrate the airfoil shape optimization into the process. And we could also study to integrate the main landing gear into the fuselage to have less constraints. So thank you very much for your attention.
Happy to take questions. A quick one from me. Was the wing area constrained in your optimization?
No, it was free. In the platform optimization, it could change.
Questions from the floor? Need some assistance.
Thanks. It's a really interesting talk. I just had a question. I think you said that you'd fixed the CG, which I'm guessing, I know you can run into some difficulties if you extend the span on a swept wing with moving the CG behind the landing gear so it's not stable on the ground. But I was just wondering how that constrained the wing and how you implemented it. Did you have to do a loop on the structural design?
Yeah, let me clarify that the center of lift. The center of lift is fixed relative to the mean aerodynamic chord. So it's the same level of stability, which I would fix for the optimization.
Okay, and the center of gravity then, did you check that stayed in front of the main landing gear on the ground? So
yes, that is all included. All the stuff is included, and this is the reason that the inboard wing needs some space. That's the reason you said for this.
Okay, but was it quite a strong constraint on the planform, having to keep that XCG in the same position? Or because as you extend the span when it's a very swept wing, it moves the CG off. So I was just, was it sort of integrated into your structural design?
And the landing gear was shifted, and from the center line to the outboard, and from the front to the back, and then the first position which the loop finds, which fulfills all constraints, was then selected for the set of given design parameters. So this was the approach behind the selection of the position of the main landing gear.
Okay, thank you.
Tobias, thanks very much.
Okay, thanks very much. It was a great talk. It was a fabulous talk. Any adjective you can use. Can you hear me all right? Can you hear me all right? Is the microphone on?
Yes. Yeah.
Okay, thank you. Now, obviously, the structural engineers and the aerodynamicists, they look at aircraft design using different lenses. They are not wearing the same lenses. My concern is your presentation appears to be dominated by aerodynamic consideration. To increase the lift and drag ratio, you cannot go on increasing the aspect ratio indefinitely. I would like to see the shear force, bending moment, and torque diagram on the wing. A compromise has to be reached. Now, the structural aspect. My concern is about the structural aspect. A typical airliner, a transport airliner, has got an aspect ratio roughly between 8 and 10, in my knowledge, The aeroplanes that I have analyzed, they have aspect ratio of the order of 9 or 10. You are trying to achieve an aspect ratio of 13, around 13 or 14, something like that. Now, can you explain to me, how do you satisfy the structural consideration? Obviously, I am a structural engineer. I am biased and maybe prejudiced against the aerodynamicist. So how do you compromise the strength consideration and the aeroelastic consideration to make sure that your aerodynamic design is viable? So a compromise has to be reached. Can you explain to us and enlighten us what are the potential difficulties and pitfalls that lie ahead to achieve your objectives?
Okay, when I understand your question right, so I think in this approach, the structural sizing minimizes the mass. So it's not from this approach, it's not clear. Is this the best solution? Maybe it could be a solution that's a little bit better with more stiffness or strength in some parts of the wing. So that's not. This is in all the steps. All the minimum mass on the structural side is here included. So that's that's right.
Okay, Ranjan, sorry, there was quite a lot of information in your question. Can I suggest that you have a discussion over coffee over this?
Yes.
We take the next question here. Thank you.
Yes, you are welcome.
Okay, Tobias, thanks very much. Just very quickly, the statement that you made that not the highest aspect ratio is the best one, is it from your expertise something that can be made for long-range configurations only?
Yes, these results are not general, so it's only for the given constraints and for the long range. So if you have other constraints in a short range, you get other results. That's right. It's not a general, but I think the approach that you make an optimization from aerostructural and find the best compromise, you have to do the same for a short range or with the constraints there.
Okay, thank you. And then final question from Jonathan.
Nice presentation. There's been quite a few other similar studies where they're saying the optimal wing size is about 15 and a half. What are you doing different in your design approach that perhaps doesn't push to such a high aspect ratio?
I think there are a lot of things other than a short range, because on long range it's important to have enough payload to bring this, and all the the mass of fuel you need, then it's not possible that you have a high level of wing mass or relative wing mass. So that's one reason, because there are some differences, and also the constraints for the integration of the landing gear, and so that also play an important role. And some other nice detail is that the load control in cruise flights to shift the lift more outboard also goes into the trimming of the aircraft, because you have a backward swept wing, and then your lift is also going ahead of you, and then you get more trim tracks. There's also things you have to consider. This could also I think it plays a role.
Okay. Thank you, Tobias. Old age, huh? Right, so that brings us on to our third talk. It's from Doug Wells. Doug has his Bachelor of Science in Aeronautical Engineering from Western Michigan University, and then his Master of Science from Georgia Tech in May 2014. An expansive career, NASA until May 2017, and then Lockheed Martin for 5 years, and then back at NASA since May 2022. So Doug, over to you.
All right. Thank you. Thank you for attending my presentation on NASA's transonic truss-braced wing studies. I want to thank my co-authors, Greg Gatlin, Jason June, and Ty Marion for their valuable contributions. They also work at NASA Langley Research Center in Hampton, Virginia. So NASA's invested a lot of time and resources into transonic truss-braced wing, or TTBW, studies. This is just kind of the outline to go through the talk today. I'm going to cover transonic truss-braced wing background. I'll talk about studies that we worked with Boeing, Virginia Tech, and Georgia Tech, and also cover some internal NASA studies. I'll finish with a summary at the end. All right, starting with background. The National Advisory Committee for Aeronautics was established in 1915 to direct and supervise aviation research in the U.S. Research continued when NACA became the National Aeronautics and Space Administration, or NASA, in 1958. Currently, there are 4 directorates. The Aeronautics Research Mission Directorate today does aviation research in areas including urban air mobility, air traffic operations and safety, ultra-efficient airliners, and high-speed commercial transports. So one of the, I guess I should say, a couple other areas that we're in now is sustainable aviation and studying technologies to enable the U.S. Aviation Climate Action Plan to achieve net zero greenhouse gas emissions by 2040 in the U.S. sector. So one of the promising configurations that may help with this goal is the transonic truss-braced wing. A couple presentations ago, saw a little bit of history on it. Sometimes it's traced back to Hurel Dubois in the 1950s, sometimes a little bit earlier. Werner Fenninger in 1970s developed a concept for a transonic truss-braced wing. He was looking at increasing the amount of laminar flow on a wing. So this is one of his concepts that he developed. I think this one's from the 1970s. So this concept was designed for long ranges and high altitudes to get the unit Reynolds number on the wing down. So a couple features of this is a high aspect ratio wing, a short chord, and a low sweep, which also help with laminar flow. That also increases risk in aircraft design, in aerodynamics, structures, and wing weight estimation. Start with some Boeing research. There's a lot of transonic truss-braced wing development and testing during the subsonic ultra-green aircraft research, or SUGAR study. This just shows the development timeline of the TTBW. This is by year and phase of the SUGAR. So starting on the left and walking through this, Boeing's involvement started in 2008 with a NASA research announcement to look at advanced concepts. There's a lot of work done during phase 1, including looking at future scenarios, selecting baselines and advanced concepts for further study. They did some detailed performance analysis. They looked at risks, technology roadmaps, and technology suites that would also be included in future aircraft. So phase 1 included truss-braced wing as one of the advanced concepts. This design was had a cruise Mach number of 0.7, which is lower than current aircraft of the same size today. And that was to reduce the amount of fuel burned during the mission. Phase 2 was used to reduce wing weight uncertainty, and it included a nonlinear aeroelastic test at NASA Langley. Phase 3, the configuration changed to enable a higher cruise Mach number of 0.745, which is still slower than similar aircraft of the same size today. It also included the first high-speed performance test in the wind tunnel. Phase 4, the configuration again changed, and the cruise Mach number, it changed to a 0.8 design, which is similar to how this size aircraft operates today. We looked at, or included, a high-speed test and the first high-lift test as part of Phase 4. Phase 5 included more wind tunnel testing, focused on high-speed buffet boundary testing, and another high-lift test. It also included a preliminary icing evaluation. Sugar is currently in Phase 6, and right now they're focused on high-lift, deep stall, acoustics, icing, and structure, so a wide range of topics. NASA is currently performing a deep stall risk reduction test, and that is based on the Phase 6 activities. NASA's been deeply involved and a part of all of these wind tunnel tests throughout the Sugar program. Also wanted to mention this, since it's also related to TTBW. NASA established the Sustainable Flight National Partnership, or SFNP, to work with government, academia, and industry to work towards the U.S. Climate Action Plan goal, and specifically to identify, select, and test technologies that can be used on the next generation single-aisle transport. So in 2023, NASA awarded Boeing the Funded Space Act Agreement, or FSAA, to develop, build, test, and fly a near full-scale TTBW demonstrator aircraft. The image on the left is from the announcement. The image on the right is just an artist rendering of what the demonstrator aircraft will look like. So NASA, as part of this, will invest $425 million over 7 years and provide access to NASA facilities and technical expertise. And Boeing and its partners will invest approximately $725 million as part of this program. So getting into Virginia Tech's research, NASA's sponsored many studies with the Virginia Polytechnic Institute and State University, or Virginia Tech's Multidisciplinary Analysis and Design Center. They've developed a multidiscipline design optimization method that includes modules for aerodynamics and wing weight estimation. They include aerodynamics and structural estimate methods that enables coupling between the two, so we can get a better estimate of wing weight for a truss-braced wing configuration. NASA is currently using this method for independent assessments and system studies. So I just wanted to highlight 2 of the studies that Virginia Tech conducted using this method. In 1998, they looked at a 777-200 size aircraft and found that there was a 29% fuel burn reduction and a 15% takeoff gross weight reduction. Then in 2012, they published a study for a 737-800 size aircraft, and that showed an 8% fuel burn reduction and 4% takeoff gross weight reduction. NASA also conducted several studies with Georgia Tech, or the Georgia Institute of Technology, their Aerospace Systems Design Laboratory, or ASDL. Recently, there was a study to look at wing weight, or building wing weight surrogate models from their aerostructural model. This was to implement a better wing weight estimate into the NASA analysis software tool. So On a different contract, they also developed an aviation technology dashboard tool. So this was built to look at different technologies across different aircraft sizes and classes. So as part of that, they developed a lot of aircraft models, and one of those was a truss-braced wing aircraft. So they developed an independent, non-proprietary TTBW aircraft that's available now. They're currently using that to look at new technologies and propulsion and fuel types. Okay, so getting into some NASA internal research. NASA commissioned a study, I think it was 2020, to look at aircraft icing research. And part of that was, one of the areas of that research was to look at TTBW aircraft. So the purpose was to assess the priority needs for NASA and enduring needs for the aviation community. That included experts from NASA's Glenn and Langley research centers. And it also involved stakeholders from industry, academia, and other government agencies. And from this study, they found 4 key challenges. One was the certification requirements may compromise efficiency goals. Comparative analysis cannot be relied upon for icing certification. Current icing simulation tools are not fully validated for relevant icing certification. So we may need some more testing. We can't rely on past icing research and apply it towards truss-braced wing. The last one here was thin wing, high aspect ratio designs pose challenges for ice protection integration. So an example is in the lower right here. It shows just some notional airfoil cross sections. Today's airfoil and a TTBW representative. It shows that the TTBW has a smaller cross section, and in the same icing condition, they're estimating that the relative ice accumulation will be larger for a TTBW aircraft. So it may need either some other icing protection systems or envelope reduction or something like that. So one of the recent studies NASA's conducted was an independent study of the Sugar Phase 4 TTBW and comparing that to tube and wing configuration. One was to verify the fuel burn benefits between the TTBW and a conventional configuration, and just use NASA internal analysis tools in order to perform that. So the results were similar to what the Boeing report showed, which is now available in NTRS, the Sugar Phase 4 report. But we found that there's 5% less fuel burn for the 900 nautical mile economic mission, and 11.4% less for a 3,500 nautical mile design mission. As part of that study, NASA created an internal FEM model using the higher fidelity conceptual design and structural optimization, or HCD Struct software tool. As part of this, you had to add the capability to analyze the TTBW aircraft. So this included being able to place the wing on top or bottom of the fuselage, adding strut and jury components to support the wings, and being able to define the contact points, the sizes and locations of those. So the FEM, or finite element model, was optimized for wing and fuselage minimum weight and strut and jury minimum cross-sectional area. So that's how the model was defined. The result from this independent study on its own was that the wing truss weight was about 4.6% less than the Sugar Phase 4 published results. So referring back 2 slides to the NASA independent assessment on the TTBW performance, those models were used in a system noise independent assessment. So NASA built a model of the Sugar Phase 4 TTBW using the Aircraft Noise Prediction Program 2 or ANOP2 framework. And this is how it was done. They estimated the certification noise levels and compared with the conventional tube and wing aircraft, and also looked at the overall noise levels. So the TTBW showed a lower community noise compared with the conventional configuration. Two of the features that contributed to this was shielding of the engine noise by the fuselage and better low-speed performance. To note, the fan element was the dominant noise source at the three certification points. NASA is planning to continue to refine this independent assessment as more studies go on. And results from this study are used in the performance systems analysis studies through either weight or drag impacts. So this is another internal systems analysis study. We call it the design exploration study. So the idea is to explore different aircraft sizes and propulsion system types, comparing similar transonic truss-braced wing to a conventional tube and wing configuration. Plan is to look at 50-passenger regional jet size, a 154-passenger single aisle, and 300-passenger twin aisle size aircraft, and apply 3 different propulsion technology or system architectures to each of those. One is the turbofan, one is a mild hybrid electric turbofan, and the third is the open rotor turbine. So all of these aircraft will be sized to meet the mission requirements and constraints, and make sure that we're doing an apples-to-apples comparison and try and look and see what benefits there are at all of those propulsion system types as well as the aircraft sizes. So the summary here, I talked about the Sugar research with Boeing that did a lot of testing and development of the TTBW concept. Talked about the X66, which will be designed, tested, and built, getting flight test data. Virginia Tech Research, which developed a MDO method to analyze the truss-braced wing concept. Worked with Georgia Tech to, mature some of the methods available in our systems analysis framework, as well as the open geometry that they have available. And then the internal NASA research in icing, noise, and the independent assessments. Just want to thank NASA Aeronautics Research Mission Directorate's Advanced Air Vehicles Program for funding this research, a lot of the studies that were conducted under this and for this paper. And I want to thank others at Boeing, Georgia Tech, and Virginia Tech, as well as a lot of the NASA researchers on all the work that's been done that I included here, and also in the research development testing collaboration for the TTBW configuration. Thanks for your attention.
Thank you, Doug. Do we have any questions from the floor? Ranjan.
Thank you. Well, if I may say so, your presentation appears to be low in technical content. The calculation element in your presentation, what you said in your presentation, I could have read it in the flight magazine or aerospace. I was curious that why you haven't given much technical information, the calculation element of your presentation. It seems to me that there is quite a lot going on behind the scene, but your presentation was simply a descriptive nature of the work, which I could have read in a newspaper or flight magazine or aerospace. Why the technical content of your presentation, the technical content is really low? Can you please explain this to me?
Yeah, so this was a lot of introduction into this design exploration study, it's leaning a lot on the studies that I pointed out here specifically. It's definitely not comprehensive. A lot of the methods that we use just for these systems analysis studies, one example is that Virginia Tech MDO framework that they developed. That includes aerodynamics estimates, their conceptual design level work. They also included the structural estimates, and I'm less strong on that area. But there's a coupling between those two in the method that they built. And so we're using that to do estimates. I pointed out a couple others that are out there that we're using as comparisons, just to make sure that we're not that far off of what may be feasible or real. So yes, there's not a lot of technical background in this presentation, but it's in the studies that were conducted.
Be coming round the other side. It's better if you do it with the mic. Thank you.
Thank you. If you compare it to the tube, as the conventional tube configuration, this conventional tube configuration is a turbulent, low aspect ratio transport aircraft, or what is the comparison when you mention the conventional tube configuration?
Yeah, so we've looked at several. One, we try to tie to a current aircraft, just it's a real flying airplane. We also usually extract that to an advanced tube and wing configuration. We extend the aspect ratio on those usually, add technologies so that they're apples to apples comparison with the truss-braced wing. With the truss-braced wing configuration, we do have higher aspect ratios. I think Sugar was in 19 to 20. So one of the recent ones was an aspect ratio 13 on the tube and wing configuration. Does that answer your question?
Thank you.
Okay.
Yeah, I just back that up. It's quite interesting when optimization tools are deployed for compare with an in-service aircraft. What does the optimization do with the existing geometry? And then when you apply it to truss brace. So, because invariably these studies do a lot better than the people who actually make the aeroplanes, or so it seems. Okay, any more questions?
Thank you very much for your presentation. This is Melike Nikbay from Istanbul Technical University. I was wondering if there is any specific reason that you don't use any non-planar wingtip sections for minimizing the induced drag further, or is this in your plans?
Not in the plans. We don't have any tip treatments. That's what you're referring to?
Yes,
yeah.
Like winglets or any kind of non-planar wingtip optimization. Was it considered?
We haven't considered those, no.
Is it in the plan? I mean,
not
or
that
you are
I
not
know
interested
of.
at all?
We haven't done that. Since this is conceptual level, we just do like basic plan forms, and we haven't done any winglets to add to that.
I thought that it would be maybe helpful in the next phase.
Okay. Yeah.
Thank you.
Any further questions?
Yes, I have also a short question. Is this planned to consider also laminar flow, because the wing has this relative shorts which are good for laminar flow? Is this planned to go in this direction or something like this?
Yeah. Sorry. The Sugar studies all included laminar flow as part of their concepts, and so we've built those in. I didn't point any out here, sorry, but we do consider some laminar flow, usually natural laminar flow, and haven't gone to like full CFD on every configuration to confirm that it's in the design, but we assume that it's there at some percentage.
Okay, anyone else? If not, let's thank Doug again for the talk, and we get a little break.
Okay, we can move to the Last speaker of this session, Professor Carlos Cesnik is a Clarence Curley Johnson Professor of Aerospace Engineering at the University of Michigan and founding director of its Active Aeroelasticity and Structure Research Laboratory. His research interests have focused on computation, experimental structural mechanics, and aeroelasticity. He has over 3 decades of experience in multi-fidelity, multi-physics modeling, design simulation, and experimentation of various aircraft concepts, spanning fundamental and applied research. Professor Cesnik is fellow of American Institute of Aeronautics and Astronautics, Vertical Flight Society, the Royal Aeronautical Society. He has several publications, including a recent book on dynamic of flexible aircraft. Please come. Thank you, sir.
All right, good afternoon, everyone. And thanks again, Sergio. This is, in order to close our 2 session on high aspect ratio wings, what I'll present this afternoon is slightly different from the first 3 papers that you saw, primarily at overall aircraft optimization levels and configuration. And this is more of a design of exploration, where we look specifically to the maneuverability of aircraft with those high aspect ratio wings. It is, I'll say the primary reason really at the end for you here is to see potentially the importance of assessing flexibility effects that are resulting from those higher aspect ratio wings, whatever that optimum might be, in order to account for the ability to maneuver the aircraft. This is a compilation of the work that was primarily done by my former student and postdoc, Divya Sanghi, another postdoc, Christina Rizu, who is currently an assistant professor at Georgia Tech, and myself. And as I'll mention at the end, this was a collaborative work with Airbus as well. Clicker. Oh, the opposite button. Okay. I'm not going to dwell on this. It's just that was put together for motivation. But you know, there are a lot of different things we need to do in order to achieve the net zero by 2050, if we can ever do that. And among them are the technologies. And this is the part we are focusing here in airframe configurations with higher energy efficiency. And this is aerostructural optimization done, where even the airfoils are designed. So in a particular fixed range aircraft here, and I can't recall exactly what was the range on the 6,000 nautical miles, or what, I can't remember exactly what it was. And this is balancing between fuel burn and mass takeoff weight. And this is, and it shows basically that if you really emphasize fuel burn, you end up with a much higher aspect ratio than we currently do, but we're going to pay a weight penalty, which can be reflecting acquisition costs, and with the lower operating cost. And vice versa, if you really focus on minimizing the weight of the aircraft, the mass of the aircraft, then you end up with a lower aspect ratio, but you have to spend more on the operation of that. And then sensitivity to technology, as we saw in a previous presentation here, the impact of that. But the point here is that the aspect ratio is really a driver for improving on the energy burn. And you see this as response from industry, right? I mean, you already have planes flying with that, planes planned to be built for this. I took the 787 as an example because it's probably one of the most flexible certified airplanes we have, at least in this class of transport airplane, where you can get to close to 28% of tip deflection under 2.5 G pull-up, based on this Boeing information here. But Boeing is not the only one, of course. Airbus has different concepts for future aircraft where they're much more efficient. You can see high aspect ratios in all of them. Embraer has very similar things in different range of application from the regional in high-end regional pieces of that. Now, when we look at the contributors to emission, really the twin aisles or the long range are responsible for half of that, more than half of that, depending on where you are, but it's about half of the total emissions. It's not going to be from the regional or the air mobility, if we can get to the numbers we were talking about, or business jets. But although all of us have to contribute to this, and we are all working towards reducing our 2-3% current participation on CO2 emissions and other emissions there, I really was trying to target here the long-haul flights. And then for that study, when we look at this and start increasing the aspect ratio, we had certain things, right? Well, first, of course, it's benefit. We get higher dynamic efficiency, which is what we are really after in terms of reducing environmental impact. So this aspect is very positive. On the other hand, we had a lot of issues due to now this larger resulting deflections of the wing, still same levels of strain as before. We haven't changed our whatever is our limit on the materials that we use. It's just a geometric effect that adds up. Therefore, our shapes are very important for everything that we do, from loads, stability, you name it. And then what happens is that we end up with higher loads, degradation, maneuverability, flutter on set, handling and ride quality. There's a lot of challenges that we have to do just because of that. Besides all the way we analyze these types of vehicles, because of the kind of tools we have been using, which rely heavily on linear aspects of the problem, and now we don't have that necessarily anymore. And to make matters worse, we have examples of this in different cases, but we can be conservative by using linear analysis, but sometimes we are not conservative. And that can happen even with the same configuration and different mass conditions. So we really cannot generalize the ability to use linearized methods in problems like that, depending on what we're after. So what we'd like to do here is really investigate the roll maneuverability in the presence of those high aspect ratio wings, which really reflecting in higher span. And try to answer these three questions here. First, the conventional trailing edge surfaces, how that will perform in the presence of those high aspect ratio wings. Can we do anything in terms of passive tailoring to improve on that or impact that? And then about different ways of doing this. You saw some presentations this morning on flare folding wingtips, particularly for maneuver and gust load alleviation, for load alleviation in general. Can we take advantage of that and maybe do something more in terms of roll maneuverability? Now, let me go back a moment. I want to point out one thing. First is that we all know that if you take mass, move away from the center of rotation, you're going to get higher rolling inertia, which is going to create lower response. So by extending the wings, there is a problem about that. The fact that we move loads outboard in principle, I know we want to maneuver loads or want loads not increasing the bending moment, root bending moment. But if we were to move that, the variation that's linear versus the other one non-linear, so ultimately we lose roll maneuverability by extending the wings. That aspect is okay in a rigid wing. What I am after here is actually the impact of flexibility, particularly the bending flexibility. And remember, these are configurations with swept wings. We're flying transonic here. Oops, wrong direction. Right, so I'm not going to dwell on the framework. I have this framework that we have developed to capture coupled nonlinear elastic flight dynamics, and we can model different effectors. I'll show you briefly the philosophy of how we model this. There are separate, a lot of papers that we have been written on this topic. But that's the framework where I'm going to be studying this. And then I evaluate this in a couple, or maybe three here, of models. I'm going to use a baseline, which will be a representation of what a commercial conceptual transport aircraft to be today, and then a modified version of that, which is re-optimized for a higher aspect ratio wing, but basically the same mission, same fuselage. And these are just representations of what it could be. And the intention here is that academically, I know we can do magic and create some really cool vehicles that can do whatever we want them to do. But in order to be representative, there's a bunch of other constraints that goes into that. Again, this is not optimizing. These things have been designed. It is really just to investigate the ability to roll them. So the simulation environment really starts from some high fidelity representation, aerostructural modeling of this. And then we have to really represent this in a geometrically nonlinear way. And because of that, and the low frequencies and a bunch of other reasons, we end up having to couple the flight dynamic equations with the structural dynamic equations and aerodynamics. So we get an enhanced set of equations with a bunch of nonlinear terms. And from that analysis, we can do different things. When we analyze this in a computationally robust and effective way, we have actually created an equivalent condensed model of the structural part plus some kind of representation of the aerodynamics in order to facilitate the simulations. Those are expensive time domain simulations. And we can still get those kinds of outputs, maneuverability, gust response, flutter, post-flutter, all of that in a reasonable level of accuracy. But remember, I want to do this connection with the high fidelity FEM CFD type of model. So we create a link, numerical link between this through reduced order modeling, be that from the aerodynamic realm or the structural realm, and then create an equivalent representation with a numerical thread that connects from the high fidelity to this low order kind of representation. And eventually, if I put this into an MDO process that we have been developing separately, I can go back and link this to alter my regular design variables in that things. Again, this is described in papers, and I'm leaving the references for you. So anyway, we're going to be doing just this part. We're going to take this model that has been reduced already for 2 different aircraft. There's the third one with the flare wingtip, but is a version of the second one. So those 2 to 3 models, we are fixing them. We're not redesigning anything. We're just analyzing them and explore the movable control surfaces there. So I mentioned about this baseline. What we took is the XRF1 from Airbus. It's a provided industrial standard multidisciplinary research test case that represents a typical configuration of a long-range wide-body aircraft. It's not a commercial aircraft. It's not one of the production aircrafts. It's just a model that Airbus uses with collaborators to study these things. It has a more conventional configuration in terms of aspect ratio. And then we had, and my colleague Kim Martins in his group has redesigned the wing for that in terms of optimizing for fuel burn. And we end up with something that's 20% longer, about 40% lower on the force bending frequency, and has more pronounced nonlinear effects. We call that the XRF1 high aspect ratio wing. And we're going to refer here by a flexible aircraft and a very flexible aircraft in the studies that you'd see. I keep clicking in the wrong direction, sorry. Now for these vehicles, we are going to be looking at 2 different flight conditions. A lower dynamic pressure, lower Mach number, and then a cruise condition at Mach 83. I'm clearly missing here an approach to land kind of flight condition. Unfortunately, we didn't get the aerodynamics for that yet, and this is still work in progress. But that will be one very important for roll controllability. We want to see how that works in low speed scenarios. But those are the 2 that you're gonna be seeing, Mach 0.65 and 0.83. And then just a basic assessment. The original aircraft or the baseline aircraft has a aileron placed there. You're going to see that in the representations. And then here is going to be a result of that under the particular flight condition. We started this by taking the very flexible aircraft, the expanded span, and then position an aileron at the same percentage span position. Okay, and I fail to remember exactly what that span position is, but you can see this is done proportional in the figure here. And that becomes important for our discussion. So here I'm going to run the simulation. This is a bank-to-bank maneuver. We'll come back to this when we discuss more dynamic results. And these are the two aircrafts are superimposed to each other here. I'm going to command at the same time both vehicles, and then you can see the response of that. The blue is the regular aspect ratio one, and the higher aspect ratio is the red. And as the simulation works for the same level of control surface deflection, the same span-wise, relative span-wise position, the response of the red one is way much slower. It wouldn't even satisfy certification requirements for that. So what can we do there? Well, first, the idea is like, where should we put the aileron? We have some rules of thumbs in terms of, first fill up with flaps as much as you need a high lift, and then we start using the rest for aileron. We decided to carry aileron throughout this, all done based on the rear spar, and segmented them, and now try to find the sensitivity of those at different stations. What do we get out of this in both of these configurations? And this is one for the lower dynamic pressure condition, or the lower Mach. And what you can see is that, I think let's look at this more conventional thing. As you move away the aileron from the center of the center fuselage, you get an improvement on the control effectiveness here, which is really being measured by roll moment, by degree deflection, and I normalize by the area of the aileron, since I'm using the rear spar as the chord, and I'm trying to give some of these lengths. The area was varying. I didn't want that to be a problem. So as you put the aileron outboard, it gets better, but eventually start reducing it. And there's some, of course, elastic effects that we have. This is zero effectiveness. You can see this in the very flexible aircraft. You end up with control reversal at some point. I also did here different levels of aileron deflections, 2, 10, and 30 degrees. If it's linear, it shouldn't matter, right? Because I'm normalizing by the degree deflection of the aileron. But in reality, it does have, particularly in this case here, some nonlinear effects that start being very, very small, but they're a bit there. When I go to higher dynamic pressure, as expected, the efficiency will drop, right? And now I not only have reversal only on the very flexible one, I have reversal also in this one. Now, we're not going to be using these ailerons in high-speed conditions anyway, in terms of it's not expected that you maneuver like that. But that was interesting to see, and then interesting to see the levels of nonlinearities that start being picked up here. A lot in here, which has some very, very strong nonlinear effects in this region there. Now, most important thing is really where the effectiveness peaks, right? And it really peaks about mid-span for this one here, and about a third or so on this. It's much inboard, further inboard on the flexible one from an absolute position, or I'm sorry, a relative position. If we look into dynamic response, so those are static things. I was looking for like terminal roll conditions, just creating moment in order to roll. But now let's bring in inertia to this. And this is the bank-to-bank maneuver. Basically, I need to cover go from minus 30 degrees to plus 30 degrees within 11 seconds, at least the FAR part 25. And we do this by rolling into one side and then reverse that and count the time. And here's a total of 60-degree variation from minus 30 to plus 30. And it should happen in less than 11 seconds. I did different, start looking different layouts of ailerons here. The baseline is where it is. I looked to one further inboard that should have more efficiency. And then for the VFA, we had the similar piece, the one that was the same percentage span as I used before in that movie, and then a couple of ones inboard of that represents better scenarios on performance. So when I look at the flexible aircraft, what we see is that, again, as expected, if you, oh, sorry, at the low Mach number, as expected, if you bring the aileron to those points where we already saw the effect of higher performance, you have a slight improvement on the roll angle as function of time, so maximum roll that is achievable. I mean, if you look at the, in solid lines for the FA, dashed lines for the VFA. And for these corresponding positions, which has the same distance from the root or from the mid fuselage line, little degradation but similar performance. Overall, lower performance for the very flexible layout. When I look at higher Mach numbers, then we start having reversal earlier on the FA, lower performance on that, as we saw on the static case. So the placement further inboard in percentage span relative to the FA is what we confirmed here. Now, we look in terms of, I mean, one thing you know is that control reversal typically has to do with torsion of the wing, torsional flexibility of it. It's something that you control, moment induced, cancel the delta lift because of nose down, and then you end up not having any resulting thing. And this is true in a straight wing. I mean, actually it's true across the board, but in a straight wing in particular, where the bending doesn't really matter. Now in a swept wing, when you bend, you naturally have a bend twist coupling, right? Because now you're bending from an aerodynamic point of view, you nose down. So this is what we are looking here. We took in this exploration just one component of the stiffness, the bending stiffness, out of plane bending on the first case, everything else the same, and then on the right case, only the torsional stiffness. So if you start from the torsional part first, if we stiffen the wing, yeah, it does improve some, as expected, but it doesn't fundamentally change this. And the increase here is on the order of 50%. I can't remember exactly what the number was. It's in the reference. On the other hand, if we change the out-of-plane bending, oh, sorry, I have it here, sorry. Baseline, 15% increase, all the way to 75% increase in the component of the stiffness in isolation. It's not a realistic case because once you increase one, you're going to increase the other. But just to see the impact of torsional stiffness versus out-of-plane bending stiffness. So you see here from the torsion, it doesn't do a lot. This is all the very flexible aircraft. On the other hand, the bending impacts significantly the problem. By not allowing the wing to bend too much, we end up having much better authority of these ailerons. Right? And the point of the sweet spot in terms of the best performance, starts moving outboard. So we can put ailerons further outboard if I actually have a stiffer wing. We can look at this in basically different ways from one of these things here. Ultimately, the placement of the aileron is really the most important one in terms of impact, but still, it's still the, oh, we're running out of time. It's still the tailoring impacts that. And then I'm going to be very quick on this last piece, which is the flare folding wingtip. Since we are using that, we may want to fit on gates and whatever. Can we do anything? Can we improve? Can I release the tips and roll the aircraft? Would that improve? There's a lot of results here. I'm going to go straight into this one here. If I take these are loads. Sorry. If I take the roll here, the reality is that if I do a flare folding wingtip for this high aspect ratio, that is this large airplane, at Mach 6.5, it basically doesn't do much of anything. It does improve the loads. This is root bending load in the center, and this is the roll angle function of time. The roll angle doesn't matter much between having the straight or this free to flare. When we increase the Mach number, increase dynamic pressure in this case, then we actually have a penalty on the roll by releasing the tip. And it became worse. And then the wingtip doesn't do anything. In terms of, what we have been finding is that flare folding wingtip for twin aisle doesn't behave the same as for the single aisle that we know that has improvements on potential improvements for loads. And then tailoring, the idea is the same. If you stiffen the wing, you get better results. So the stiffer you can have, if you can make it, again, this is not optimized for weight. This stiffness is going to come with a weight penalty. Overall system design is critical here. So, try to answer the questions of what can do with the trailing edge. By the way, I also investigate leading edge. It didn't help much, for my surprise, but at least. We saw that for maximum effectiveness, about 50% of the semi-span is where we want to put the flaps from purely performance point of view. But also, if we can actually do some increase in bending stiffness, we can move this further outboard. And we can certainly improve the control effectiveness. And then in terms of the flare folding wing tip, if we have lower dynamic pressure or equivalent stiffer wings, yes, we can do better in terms of maneuverability. It does improve releasing it. But if we have higher dynamic pressure, releasing it is not doing much for the roll, and in fact not for the load alleviation that I haven't discussed here. Bottom line is that accounting for flexibility is an essential aspect of assessing benefits of control effectors in any future high-performance aspect ratio aircraft. And I want to close by thanking Fabio Vetrano from Airbus, who helped us a lot in CFD data that came from that study. This was part of these things I showed you as part of our Airbus Michigan Center for Aeroserve Elasticity of Very Flexible Aircraft. And last but not least, I'd like to thank Airbus for providing the baseline XRF1 result. Thank you, guys.
Thank you, Carlos. We have time for a couple of questions. Sorry, first one.
Thank you, Carlos. As always, it is nice and lovely to listen to your presentation. It is always a pleasure. Now, structural nonlinearity versus aerodynamic nonlinearity. Understandably, the importance of these nonlinearities are recognizably at a different level. Can you comment on the impact of both the structural nonlinearity and aerodynamic nonlinearity in the design of high aspect ratio wings? These two nonlinearities, they take their effect in different ways.
Yeah.
Now, in my opinion, if you have to give some priorities, perhaps some of the areas are more important than the others. Can you comment on this and give us your insight?
Sure.
How these nonlinearities, they reflect in the design?
Yes, yes. We certainly have both, right? We have both the structural nonlinearities from a geometric point of view as well as the aerodynamic. And the aerodynamic here comes in different flavors. So we certainly, it's a transonic flow, so you certainly have the usual, let's put nonlinearities coming from transonic flow. But in the case of a problem where structurally is geometrically nonlinear, you have to also geometrically nonlinear carry on the loads. So you cannot use a reference configuration for evaluating your aero forces or inflow conditions or whatever that might be the case. You have to always use the current configuration. And that creates a bit of a difference. In a typical CFD-CSD coupled solution, that comes naturally. In some other ways of applying this, you have to actually force. So a Nastran air elastic solution wouldn't do the job for you in scenarios like this. But both of these contributors, the structural geometric nonlinearity is really the driver, in a sense, for most of these things. Yeah, Fred.
Yes. Yeah, thank you for your presentation. I think after your presentation, I become curious about swept forward. So what would be interesting to continue this work in that direction and see what happens.
Yeah, that would be. I haven't actually seen, and maybe people here are most familiar than myself in terms of look again into swept forward. I think after the X-29, we stopped doing most of these investigations. Yeah, it will be an interesting thing to see. Thank you.
Thank you, Carlos. You mentioned several times tailoring in your slides. Are you talking composite tailoring or?
Yeah, composite tailoring from a perspective that if I want to play with the composite properties of this and emphasize stiffness on some directions versus other, can I do that? So I can put more fibers at 0 and increase bending by impacting the other one. So as I said, this was not an optimization problem per se. I had already things designed and I was doing sensitivity studies. Basically, I was varying things, perturbing, not small in the case of 75% on the stiffness, but the idea is that we have done studies on automated fiber placement in a toe steering one, so we know we can play with the directions on things. It will be another step, and of course, it's not going to be the same impact that you can see when you have everything varying in one way. But for us, it's just to guide. Do we care? I mean, typically we think about aileron performance with torsion, and this is a problem where the torsional stiffness, I mean. This is a problem, at least for me, indicating that, yeah, torsion still plays a role, but not as big as bending. If we can actually control the bending, and by the way, I'm doing this passively. I'm sure a bunch of you are active folks who may want to actively bring in the swing, hold shape, and then maneuver about that. I mean, it's an equivalent way of stiffening the wing. You don't have to stiffen this passively. So there are different ways of solving the problem, potentially. Right?
Thank you.
Thank you once again, Carlos, for your nice presentation.
Thank you.
Please. Just to conclude this session, let me thank all the presenters, 9 today with a very nice presentation, and also the attendees for this very interesting session. And a special thank to Professor Atkinson that accepted and shared the idea to have a fully dedicated session on high aspect ratio wing. Enjoy the coffee break and the rest of conference. Bye-bye.